Okay, we're going to wrap up Chapter 8 with our final section. We have already learned about the basics of confidence intervals and how to estimate a population proportion. In this section, we're going to learn how to estimate a population mean. So, we're going to construct and interpret confidence intervals for means, find sample sizes, and lots of other fun stuff. So let's jump right in. So, some different types of confidence intervals. The one we did in the last section, 8.2, was a one sample z interval for a population proportion, given by this formula right here. Remember how we use p hat instead of p because we don't know what p is. That's what we're trying to estimate for. Now, there is also a one sample z interval for a population mean. So instead of using p hat, we are using x bar, and instead of using this formula, we're using this one. No matter which one we're using, though, we still need our conditions to be met. Remembering what those were. If it's random, data needs to come from a well-designed either random sample or a randomized experiment. Either one is fine. For normal now, we need to either have the population be normally distributed and then the sampling distribution will be normal, or if the population distribution is not normal or it doesn't tell us what it is, then we have to use the central limit theorem, and we say that the sampling distribution will be approximately normal as long as n is sufficiently large, and we always look for a sample size of at least 30. And then for independent, we hope our individual observations are independent. Okay? If it's coming from a random sample, we're usually sampling without replacement, and so the sample size should be no more than 10% of the population size. Now, we don't need to check the 10% condition when it comes from an experiment, okay? If it's coming from an experiment, then we can just assume that our observations are going to be independent. But if it's coming from a sample, a simple random sample, that's when we check our 10% condition. So kind of keep that in the back of your mind. So let's go ahead and see if we can determine a minimum sample size. Okay, so the margin of error of a confidence interval for population mean is given by this formula right here. We've got our critical value z star and then our standard deviation of our sampling distribution formula right there. We determine a sample size for a desired margin of error when we estimate a mean, basically the same way when we were estimating a proportion, just now using different formulas. So let's do an example together. Researchers would like to estimate the mean cholesterol level mu of a particular variety of monkey that is often used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter of the true value of mu at a 95% confidence level. A previous study involving this variety of monkeys suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. So according to this formula right here, we need to know a couple things. We need to know our critical value, z star, and then we also need to know the standard deviation. So for 95% confidence interval, the critical value is 1.96. Either you have that number memorized, or you had to use your table, or you could have done inverse norm, right? So it would have been, what? Half of 5%, so 0.025 is what you would have looked up. And then for standard deviation, we're going to use 5 as our best guess because it came from a previous study. Probably not the true population standard deviation, but it's going to be our best guess. So now we go ahead and we plug it into the formula. So here's our z star, standard deviation, and 1. Where did 1 come from? They wanted the estimate to be within 1. So that's where that came from. And now here's some algebra. Essentially you're cross multiplying. So this 1 goes down here, the square root of n goes to the other side. If we want to get rid of the square root, you have to square both sides. And you end up getting 96.04. So n has to be greater than or equal to that. So that means we have to round up to 97 to make sure that our margin of error is no more than 1 at the 95% confidence level. So make sure you can do that algebra. One more example that I want you to try on your own. Administrators at your school want to estimate how much time students spend on homework on average during a typical week. They want to estimate the mean at a 90% confidence level with a margin of error of at most 15 minutes. A pilot study indicated that the standard deviation of time spent on homework per week is about 154 minutes. How many students need to be surveyed to estimate the mean number of minutes spent on homework per week? So go ahead, pause this video, and see if you can calculate the sample size that you need. You should have used a critical value of 1.645. That is the appropriate z-star for a 90% confidence level. Your standard deviation, we should have been using 154. And then all of that will be less than or equal to the margin of error, which was 15. If you use 1.645, you should have ended up getting 285.2-ish. And then that's going to round up to 286. Okay? All right. So what happens when we don't know the population standard deviation? Chances are we probably don't know the population standard deviation. If I don't know the population mean, how in the world would I know the population standard deviation? So when our sampling distribution of our sample mean is close to normal, we can find probabilities involving that sample mean by standardizing. That's what this z-score formula is for. Okay? So when that happens, we go from this beautiful thing to my standard normal curve. But that's when I know sigma. When we don't know sigma, we can estimate it using the sample standard deviation, right? That's my S sub x. But then what happens when you standardize it then? This new statistic does not have a normal distribution. So now we're going to be using, instead of a normal distribution for z, we're now going to have a t distribution. Okay. Now, when we use z-intervals and we know the population standard deviation, the z-score falls within the expected ranges. That's what we can see in this graph right here. So here's when I know the standard deviation of the population. Most of my data is, in this normal curve range. It's centered at 0, and it's not too far out. But when we try to use the z-intervals with an unknown population standard deviation, and we instead use the sample, it falls outside of the expected ranges. So these are parallel dot plots here. You can see it's still the same center, but the spread is much, much, much wider. It's a greater spread. And that's why we have this new distribution for t. Now, a t statistic has the exact same interpretation as a z statistic. It's still the distance an observation is from the mean in terms of the standard deviation. So before, if you had a z-score of -2, that meant you were 2 standard deviations below the mean. If I have a t-score or a t statistic of -2, it still means I am 2 standard deviations below the mean. Something that's different, though, compared to my normal curve, each sample has its own unique t distribution. Whereas with z, there was just one curve. These different distributions are going to be named by their degrees of freedom. Now, what the heck is degrees of freedom? When we're using a t distribution, we're going to subtract 1 from the sample size in order to find the correct degrees of freedom. If you have taken AP Biology, you probably are familiar with degrees of freedom because you've done stuff with chi-square. Someone explained degrees of freedom like this to me once. Say you have 10 people and you have 10 chairs, and everyone enters the room one at a time. The first person has 10 chairs to choose from, but then once they sit down, the next person only has 9 chairs to choose from, and so on down the line, until you get to the second to last person. They still have a choice, even though there's only 2 things left, but that final person, that 10th person that comes in, they have no choice. There's only 1 chair left, so that is where they have to sit. So out of the 10 people, 9 people had the freedom to choose where they sat, and 1 person did not. So that's why we have degrees of freedom as n minus 1. So let's talk a little bit more about this t distribution. Let's talk about the socks. The shape, it's symmetric, and it is unimodal, but it's not quite normal. However, it does approach the standard normal distribution as your degrees of freedom increase. So you can kind of see that by this graph here. The light blue one is the standard normal curve for Z. All the other ones are T distributions depending on what the degrees of freedom are. So they're really similar, but you can see how as the degrees of freedom decreases, my variation increases, right? It gets higher probabilities in the tails and lower in the center. Center is still at 0, right, since it is a standardized score. And then the spread, like I said, is greater than the standard normal distribution, but it gets closer to normal as my degrees of freedom increase. Something interesting, sometimes this is called student's distribution instead of a T distribution. There's a guy named William Gossett, I believe. He's the one that's attributed with finding out about T distribution. It's actually a really interesting story. He figured it out when he was working at the Guinness factory in Ireland, and they were taking really small samples, and he was noticing that it wasn't reacting or it wasn't creating a normal distribution like he expected it to, and that it was a different distribution. So if you ever have some free time, you should look up William Gossett and students distribution. It's kind of a fun story. Now, like I said, several facts when you're comparing the normal distribution to a T distribution. It's similar in shape, right? We just said that. The spread is a little bit greater. Distributions have a little bit more probability in the tails. And then as the degrees of freedom increase, it approaches the standard normal curve. Okay. Now, say you want to find this now critical value for T star. So it's not Z star anymore, it's T star. So say you want to do a 95% confidence interval for a mean of a normal population based on a simple random sample of size 12. Couple things you need to do. So now we're using this new table. Look at the very bottom row and find where it is. Well, before you do that, first you need to find the row that you need for degrees of freedom. So since our sample size was 12, degrees of freedom is 11. So we go to row 11. And then you're going to move across that row to the entry that is right above the 95% confidence level. And then see where those two overlap. So your desired critical value is 2.201. Okay. So let's try another one. So say you want to do a 90% confidence interval for a mean of a normal population, random sample of size 10. What critical T star value should you use? Well, if n is 10, degrees of freedom would be 9. Yep. And then go ahead and use your table. See where it lines up with 90%. So look on your table. You should find that it's about 1.833. 1.833. Now, if for some reason that your particular degrees of freedom is not in that table, this is table B, you're going to round down. So for example, if your degrees of freedom is 39, but there is no 39, go to the next one that's there, which is 30. You can also use your calculator. Just like we used inverse norm to find the Z, we're going to use inverse T to find the T score, or the critical value for T. So go ahead and use your table to figure out these next two. Assuming they're normal. So you need to note what the degrees of freedom are, and then using your table, find the T. In our next video, we're going to walk through a 4-step process and actually do a confidence interval for population means.